Today we start a new chapter to talk about determinants or the determinant of a matrix A. Now, the setting for this chapter and the next, so for determinants and then eigenvalues, eigenvectors, requires that the matrix A be square. So we are going to be considering a square matrix. Determinants exist only for square matrices. Now, what is the determinant of a matrix? First, notation, several ways to denote the determinant. The determinant of A can be denoted by det A, or you can put brackets around A, or you can use sort of an absolute value sign, so vertical lines around A. So this is the notation. The determinant of a matrix is a number that tells us important information about the matrix. Now, some of the applications of determinants, some of the things that a determinant would tell us is if the determinant is 0, then A is singular. Similarly, if the determinant is non-zero, then A is invertible. So this is one of the things we can use determinants for. Another thing is we can use determinants to solve the standard problem of AX equals B. So we can do that without elimination. Another thing we can use determinants for is so they have an interpretation when the edges of a box are the rows of a matrix, then the volume of the box is the absolute value of the determinant. So determinants can be positive and negative numbers and 0. So these are some of the things of why we want to study the determinants. And now one more thing, which is going to be the entire chapter 6, is we have to use determinants to compute eigenvalues and eigenvectors. So determinants define eigenvalues. This last part, I don't expect you to be able to understand it right now. You don't know what is an eigenvalue, what is an eigenvector. We will do that in the next chapter, but the point is that we require to understand, we need to be able to compute determinants so that we can do the next chapter. So this is a very important tool to understand. Now, there are 3 ways to compute a determinant. So 3 ways to compute a determinant. The first way is using the properties, and that's exactly what we will do today. Another way is using the big formula. This involves permutations. it's a revealing formula about what determinants are. Not something we normally use, though, I have to admit. And the third way, which is fairly commonly used, is using the cofactor formula, or using cofactors, I guess. Now, today we're going to talk about the properties, and we will leave 2 and 3 for tomorrow. So we'll introduce the big formula and how to compute the determinant using cofactors. We'll do those things tomorrow, and the day after we'll talk about applications of determinants. All right, now let's start with the properties. There are 3 key properties that define the determinant completely. But with those 3 properties, we can come up with several more that will make things easier. So we will summarize some of the results of those properties to make it easier for us to compute determinants. So rule number 1 says that the determinant of the n by n identity matrix is 1. This is very, very important. So the identity matrix is sort of a building block for us. These vertical lines. So if I were to write this, I would be talking about the identity matrix. By writing vertical lines around the matrix, so only vertical lines, I'm talking about the determinant of the identity matrix. This determinant is just a number. That number is 1. That's the rule. So when you have the identity matrix, you know what the determinant is. You can have a bigger determinant matrix. You can have a bigger identity matrix. The size is not important. And you will always get that the value of the determinant is 1. Now the second rule. So the first 3 rules, they're like you can think of them as a definition. You're not trying to prove them. These are your axioms. This is what you assume that the determinant does. And then using those 3 properties, we're going to show quite a bit more. So this is how we essentially define the determinant. You can think of it that way. Now, the determinant changes sign when 2 rows are exchanged. Now, with this rule, you actually can compute the determinant of all permutation matrices. So I'll just write this for a 2 by 2 matrix. Say if you have A, B, C, D. So A, B, C, D has a determinant, whatever that determinant is. By the end of today, we will know how to compute the formula for this. And I know some of you already know it. Now, this determinant is minus the determinant when I change the rows. Okay, so a row exchange changes the sign of the determinant. And as I said, we now know the determinant of all permutation matrices because they come from a row exchange of the rows of the identity matrix. So another example could be if you have this matrix, you know that the determinant of that matrix must be -1 because it is minus the determinant of the identity matrix, right? We have a single row exchange. Now, what about, say, this matrix, just a bigger permutation matrix? You see that if you exchange the first two rows, you're essentially going back. So if I exchange the first two rows, if I exchange the first and the third row, I go back to the identity matrix, and I know that the identity matrix has a determinant 1, and so I have -1. I could also look at, say, a 4x4 matrix where I have 1 here and 1 there, and then 1 here and a 1 there. So what is happening here, perhaps it's not easy to see, maybe I'll just write some zeros. So what I've done here is actually two exchanges. I have exchanged row 1 and 2 of the identity matrix, and then rows 3 and 4. So I have two exchanges, but each exchange flips the sign. You can think of it that way. So actually, this is just one. Because when I carry out one exchange to restore the first and second rows of the identity matrix, I will have flipped the sign to -1. And then, or I will have flipped the sign to minus. And then another row exchange of the third and fourth row will flip the sign one more time. And so this matrix actually has determinant 1. Ultimately, we know how to calculate the determinant of any permutation matrix with rule number 2. All right, rule number 3. The determinant is a linear function of each row separately. This part over here is very important, and I'll explain what it means through the examples. So what are linear operations, so that I can say linear function? Linearity, so far we've mentioned it many times. It has to do with multiplication by a scalar or the addition of two things. So for example, the first part of this would be multiplying or multiplication by a scalar. Now, let's say we started with a matrix A, B, C, D. Okay? I want to talk about its determinant. I want to multiply by a scalar t, for example. Now, what does it mean here when I say linear function of each row? Well, each row separately. It means that if I multiply only one row, say the first row, by the number t, the determinant is linear there. So if I multiply here by t, so only the first row is multiplied by some number t, then what I get is t times the determinant of the matrix A, B, C, D. So linearity in one row means that if one of the rows is multiplied or has a common factor, you can factor it out of the determinant. Similarly here, if both rows were multiplied by t, I would be able to factor out a t from each row. So if I have t, a, let's make those closer, tb, tc, or maybe even not t, let's call it s. So the second row is multiplied by another number. Then you can factor out t from the first row. You can factor out s from the second row, and then you have a, b, c, d. So that's what linearity in each row separately means, right? You can factor out both of these. And maybe for visualization, I will change these. Give me a second. So let's put a t here so that we can see it better. and an S there. You see, you can factor out a common multiple from each row and nothing has changed. I'll put these right here. So those are two examples. Now, so we said linearity has to do with multiplication by a scalar, and linearity also has to do with addition. So addition in one row. Let's say I will add row 1 of A to row 1 of some A prime. So let's say we have this. We have A plus A prime, B plus B prime, C, D. So I want to show how is this connected to the determinant of the matrix A, B, C, D, and then what happens with A prime, B prime, C prime, D prime. So you see, here we have a linear combination, right? You can think of this as the rows A, B added to the row A prime, B prime. So you think of this as A, B plus A prime, B prime, right? We have two rows. So what do we do with that linearity? Well, linearity means that determinant equals the determinant of A, B, C, D plus the determinant of A prime, B prime, C, D. You see, this second row stays fixed. It is linearity in only one row that we're applying. So your matrix doesn't have to be 2 by 2 and can be 10 by 10. If one of the rows is a sum, and in fact you can always take it to be a sum, the point is that you can always split one row of your choice for whatever reason into a sum of two determinants. So for example, how can we show, what example could I possibly show you? Let's say we look at 1, 1, 1, 1. What would I do here? Well, I could split the first row as a sum of two rows. So I only know how to compute really the determinant of the identity and the determinant, so far, the determinant of the identity, and I know how to compute the determinant of a permutation matrix. Actually, to make things simpler, maybe I'll just put a 0 here. Okay. Now I could look at the first row and add it. So this A and A prime are sort of up to me to choose. So I could think of A and B as 1, 0. So I could say this is 1, 0, and then 0, 1. The second row stays the same. And then the first row could be 0, 1, 0, 1. All right. The first row is the identity matrix. So this is what linearity is saying. You see, if I add the first rows of the two matrices, I will get back to 1, 1, right? So here, it seems I know how to compute this determinant, but now what about that determinant? So what is this determinant? So far, I don't know, and that's okay. Not too bad. It's okay to not know what that determinant is. We'll compute that in the next rule, although we do have the tools to do it just yet. So how do we, but the point is that the second row stayed the same, and it is the first row that I got to split somehow, that in a way that was convenient to me. Now, what is this determinant? This is actually the next rule. We can use the second rule to compute the determinant of that second matrix. You see, the determinant of 0, 1, 0, 1 is the same as minus the determinant when I change the two rows, 0, 1, 0, 1, right? So actually, this determinant is equal to minus itself. Well, that means that, if you have A equals negative A, that just means that A must be 0. So actually this determinant is 0, and that's exactly the next rule. So here, this determinant is 0, this determinant is 1, and so I know the determinant of this triangular matrix to be equal to 1. All right. The idea with the three basic rules, which are the ones I've just listed, is that we can actually use elementary row operations to calculate the determinant. And that's kind of what we want. That's the easiest way to compute determinants when working on a piece of paper. Actually, elimination is faster than using the formulas. All right, now let's look at rule number 4. So rule number 4 is exactly what I just stated. Or sorry, that would be rule number 5. So rule number 4, if two rows, I guess I just stated that. I'm getting confused with myself. If two rows of A are equal, then the determinant is 0. And I just proved that on a single example. So if you have the 2 by 2 matrix with row AB and then another row AB, what you know is that this is minus the determinant. Okay, I'm going to write this with color so that you can see what I'm doing exactly. Okay. So I'm switching the rows, right? This is now the blue row and this is the black row, right? So by rule 2, if I flip two rows, if I exchange two rows, the sign of the determinant changes. Well, again, this is what I said is determinant of A equals minus determinant of A, but determinant of A is just a number, so that means the determinant of A must be 0. And this is the case for any size matrix because you can do exactly the same trick. When you exchange the two rows, you haven't really changed the matrix, and therefore you have the determinant being equal to 0. Now, this is of course consistent with the fact that if we were to carry out elimination on the matrix A, we would get a 0 row, which tells us that the matrix is singular or not invertible. So this is kind of the first hint to that rule. If you have equal rows, you get 0. And in fact, you have something stronger. You could do the same, not with just the determinant, not if just the rows are equal, but rather even if the rows are multiples of each other. So if I have A, B, and then T times A, T times B, for example. So the second row is T times the first row. Well, remember that I can factor that T out by the previous rule. So I have linearity in the second row. I can do this. And then essentially I have two rows that are equal. I have a determinant of a matrix with two equal rows. I know that that determinant is 0. So in fact, if you have one row to be a multiple of another row, you actually again get the determinant to be 0. All right, now rule number 5. So this is actually a combination. Let me write it. Subtracting a multiple of one row from another leaves the determinant unchanged. This is perhaps our most important rule because this is exactly what we do when we carry out elimination. And this rule says that if you carry out elimination, an elementary row operation where you just subtract one row from another, you have not changed the determinant. So elementary row operations are allowed. I think we're going to need a bit more space here, so bear with me. Okay, now to give you a picture of what this looks like. So if I have the matrix AB, and then, so let's say we started with, I want to be able to relate to this matrix, to ABCD. Now from ABCD, now imagine from the second row, I have subtracted a multiple of the first row. So let's say I have C minus TA and D minus TB. So I have essentially removed or subtracted T times the first row from the second row. So like R2 minus T times row 1 into row 2. Imagine I've done something like that. That's exactly what I'm doing here. So the claim of the rule is that this is exactly equal to the determinant of A, B, C, D. Question is, why is that the case? So let's go back. We have A, B, C minus TA, D minus TB. By linearity on the second row, I can split this matrix into the following. I can split and take A, B, C, D here, and then plus AB, and then what I have in the second row is negative TA, negative TB. Well, we just showed above, if T is a number, negative T is also a number, right? That's nothing interesting there. We just showed above that this is equal to 0 because the second row is a multiple of the first row. So this is very, very powerful. It tells us that we can carry out elimination and we will have not changed the determinant. So in fact, from here, I know how to compute the determinant of certain matrices. It means I can I'm going to always be trying to get to maybe a triangular matrix or a diagonal matrix. In fact, perhaps here I should have said from this rule over here, we already know how to compute the determinant of any diagonal matrix. But that's another rule. So, of course, the first three rules give us everything. All right, rule number 6. A matrix with a row of zeros has determinant 0. Okay, so here's a visual example on a 2 by 2 matrix, although the matrix can be bigger. So what I'm saying is that if I have a row of zeros, my determinant is equal to 0. And so it doesn't matter which row I have. I could have A, B, 0, 0, and that would also be equal to 0. Now, how can we show this? Well, an easy proof would be, we know that if we add a row to, so by, okay, which rule? This rule. I want to use this rule, right? I'm going to add an A prime and a B prime to the row of zeros, right? And I know how that will look. So what I'm saying here is that I could add the second row to the first, right? I know that that this determinant is the same as the determinant when I'm adding CD to it, right? This is actually the previous rule, not the one I had showed you, not 3, but they're all combinations. So I've added the second row to the first row, and by the previous rule, that means that the determinant is unchanged. So whenever you get a row of zeros, you know that your determinant is 0. All right, rule number 7. If A is triangular, So that means upper triangular or lower triangular. Then the determinant is just the product of diagonal entries. So A11, A22 times ANN, the product of diagonal entries. Okay, so let me write that. If I have A, B, 0, C, I know that the determinant is A times C. And if I have A, 0, C, D, then the determinant, oh, I guess this should be a D. The determinant is again A times D. So the off-diagonal terms don't play a role. They don't come into play. It is really just the diagonal terms that come, the pivots, right? The pivots. So this is very promising because we are allowed to do elimination without any penalty. And we are allowed to bring a matrix to an upper triangular form, which is normally what we do with Gaussian elimination. And once we do that, we already know what the determinant is. So how are we going to, how to show that this is so? We can show that by subtracting. I mean, this kind of comes from a diagonal matrix having the determinant. So, okay, when a matrix is both lower triangular and upper triangular, then it is diagonal. So actually diagonal matrices come into play here. So let me first convince you that if I have a diagonal matrix, then the determinant is truly the product along the diagonal terms. This is the key point here. So if I have the matrix with A and D along the diagonal and zeros everywhere else, then how can I compute the determinant using the first three rules? Well, I can factor out A. A is a common multiple along the first row, and D is a common multiple along the second row. So I know that I have A times D times 1, 0, 0, 1, right? So by factoring out what is along the diagonal, I have that times the determinant of the identity matrix, which we know to be equal to 1. Now that we know that the determinant of a diagonal matrix is the product of the diagonal terms, and note here, A or D could be 0. If you have a 0 along the diagonal, then you will you'll actually have a row of zeros. But that is not contradicted by this formula, because if A is 0, then this whole thing is 0. This is 0, right? It's not a contradiction. Now, how can I use this for a triangular form? Well, here I can use the back substitution step, or use this pivot to eliminate B here. So if I do the first row minus a multiple of the second row, in order to get a 0 here, I know that such an action does not change the determinant. And similarly here, I can use this pivot to eliminate underneath, get a 0 instead of C. In fact, whatever the step is, this D will stay unchanged. And same here, this D will stay unchanged. No matter what kind of operation I take, because of this 0, A will stay what it is. So in fact, I can just eliminate B, I can eliminate C, and I end up with the determinant of this diagonal matrix. So this will be most of the time our strategy. Get an upper triangular form, and then so start with a matrix, carry out elimination, but you have to be careful that you carry out elimination according to our algorithms, because if you multiply a row by a number, that changes the determinant. But if you subtract a multiple of one row from another, that keeps the determinant the same. So you start with a matrix, you carry out elimination, you get to an upper triangular form, and then you simply multiply the terms along the diagonal to get your determinant. Now, couple more rules. Rule number 8, if A is singular, I kind of already wrote this, if A is singular, then the determinant of A is 0. And if A is invertible, then the determinant of A is not 0, right? And the proof for this is fairly simple, and it comes from the fact that we know that if a matrix, we start with a matrix, how do we know to check for singularity or invertibility? Well, we carry out elimination, right? And if we come to an upper triangular matrix that has all of its pivots, because remember, we are in the world of square matrices here. So if elimination takes us to an upper triangular matrix that has all of its pivots, then we know that the determinant is the product of those pivots. Or in all cases, you could say the determinant is the product of the diagonal terms. If there is a 0 along the diagonal terms, you get a 0 matrix. That also indicates a 0 row, which also indicates that the matrix is singular. And if the matrix is invertible, that means that all diagonal terms will be non-zero, all pivots will be non-zero, and we will get the determinant is not equal to 0. So this is already sort of addressed. Rule number 9, so we have 2 more rules to go. The determinant of the product AB is the product of determinants. So we have the determinant of A times B is the same as the determinant of A times the determinant of B. Note that this is not, that a determinant of A plus B is not determinant of A plus determinant of B. So this does not follow for addition. The proof is a little maybe too much for us, so I'm going to skip it. So this is something that I really want you to learn and keep in mind. And the rule number 10, this is actually a very important rule. It says that the transpose of A has the same determinant. So what I'm saying is determinant of A transpose is equal to the determinant of A. How can we show this? It's actually not difficult to show. So remember, A is a square matrix. We know that A perhaps does not have an LU decomposition because it may require row exchanges, but we know that we can always write P times A equals L times U. So if A doesn't require row exchanges, then P is just the identity matrix. But if A requires row exchanges, then we sort of record or store all those row exchanges in P, exchange the rows that need to be exchanged, and then we have an LU decomposition. Now, the determinant of P times A is exactly the determinant of L times the determinant of U, because, and then determinant of L, if you recall, L always has ones along the diagonal. So it's a lower triangular matrix with ones along the diagonal. Determinant of L is equal to 1. And similarly, if you look at L transpose, it will be an upper triangular matrix with ones along the diagonal. So that one really, in fact, you imagine here, this rule is definitely true for triangular matrices. That's kind of what we're going after. So if you have a matrix, well, it doesn't have to be ones, like A, B, C here, and some non-zero terms there and zeros here, right? When you take the transpose, the diagonal terms don't move, the zeros come here, and the non-zero terms come there. Now the non-zero terms it's irrelevant what they are. You see that the determinant on the left-hand side is the same as the determinant of the right-hand side. It's just A times B times C. So for triangular matrices, this rule is sort of obvious because it really just means you go from a lower triangular to an upper triangular, but the diagonal terms stay the same. So the same will be true for U here, L and U. We know that the determinant of L transpose is the same as the determinant of U transpose. Now, what we have here is, so let's transpose this. We want to reach A transpose. So what we have is A transpose times P transpose equals U transpose times L transpose, right? Now, what about the determinants? So I want to use these two equations to compute the determinant of A and to compute the determinant of A transpose. Now, from the first, so from PA equals LU, we have the determinant of P times the determinant of A equals the determinant of L times the determinant of U. From A transpose P transpose equals U transpose L transpose, we have the determinant of A transpose times the determinant of P transpose equals the determinant of U transpose times the determinant of L transpose. Now remember my comments. For triangular matrices, we know that this rule holds by just what the transpose does. So we know that the determinant of L and the determinant of L transpose are the same. We know that the determinant of U is the same as the determinant of U transpose. So really what we have is equality here. We have that the determinant of P times the determinant of A is the same as the determinant of A transpose times the determinant of P transpose. Okay, I will write that right here. So we have determinant of P times the determinant of A equals the determinant of A transpose times the determinant of P transpose. And of course, I can, these are all numbers, so I can rearrange them however I like. Now let's think about the determinant of P and the determinant of P transpose. Now P is a permutation matrix, right? If you recall, the columns of P are orthogonal, so we know that P transpose times P is the identity matrix. So for any permutation matrix, we know this to be true. Now, by using the product rule, so rule number 9, we have that from here, we have that the determinant of P transpose times the determinant of P must be the determinant of the identity matrix, and we know that the determinant of the identity matrix is just 1. We further know that the determinant of a permutation matrix is plus or minus 1, right? Because it only consists of row exchanges of the identity matrix. So we also know that the determinant of P is plus or minus 1. And by the way, P transpose is also a permutation matrix. So we also know that the determinant of P transpose must be plus or minus 1. So the question is then, do they have the same sign or do they have a different sign? Well, if you need to have the product be equal to 1, and you know that these numbers are either plus or minus 1, you know that they both must be either 1 or negative 1. So in fact, we know that the determinant of P transpose is equal to the determinant of P. We know that the two matrices must have the same determinant, either a 1 or a negative 1. So then going back here, right, we see that we can sort of divide, if you like, by the determinant of P, and these two things cancel out, and we are left with the determinant of A being equal to the determinant of A transpose. I guess one final thing, and perhaps I should have mentioned that in the previous rule. So from here, from the determinant of AB equals determinant of A times the determinant of B, the most important conclusion perhaps is that the determinant of A inverse is 1 over the determinant of A, right? So if we know the determinant of A, we know the determinant of A inverse. If A is non-invertible, determinant of A would be 0, and you cannot really divide by 0, so determinant of A inverse would not make sense. All right, now in the next video, all I'll do is a bunch of examples on how to put all of these rules together to compute determinants.